This is Dr. Holt. This lesson is on energy, a follow-up to our lesson on work. Energy is one of the most important unifying concepts in science. All physical processes involve energy. The definition I want you to remember for energy is the energy of a system is the measure of its ability to do work. There are different types of energies. The ones that we're pretty much going to work with in AP Physics are going to be kinetic energy and potential energy. Kinetic energy has to do with anything that's in motion, while potential energy usually has to do with the energies having to do with the separation between two objects that attract each other. This could be like a gravitational type of traction between two objects. And the third one, which we don't do in AP Physics, is going to be thermal energy, which has to do with more with atoms, molecules, and ions of the system that's closely connected with the temperature of the system. When forces do work on a particle, the result again is a change in the energy associated with the motion of the particle, or the kinetic energy. To evaluate that, I've gone through a simple proof. We use Newton's law, F equals ma. So I said that the net force in the x direction is equal to mass times acceleration in the x direction. Went back to our kinematic equation that Vf squared is equal to Vi squared plus 2 times the acceleration in the x direction times the displacement in the x direction. What I did here is divided by 2, and then again the acceleration times the displacement of the x. I took out the acceleration, or solve for acceleration here, which would be F over m, substitute it back in right here, and now I have to Vf squared minus Vi squared over 2 is equal to my net force divided by mass times my displacement. Multiply both sides by mass here, and now look what happens. What happens on this side over here is, this is the definition of work. Force times distance here. So I pull out the 1/2 and I have 1/2 mv final squared minus 1/2 mvi squared is work total. Now this is defined as the work kinetic energy theorem, where you have 1/2 m the mass times the velocity final squared minus 1/2 the mass times the initial velocity squared is equal to the change in kinetic energy, or the definition of work. Now, when force is constant, you're going to find out you're going to get yourself into usually into an integral, or figure out a way to find the area under the curve, but the area in the curve is not going to be constant. We often see this when we're dealing with, let me mark this, with spring forces. Also, in addition, the gravitational force the Earth exerts on a spaceship is inversely with the square of the center between two objects, so that can change too. So let's look into a problem. When the force is constant, all we're doing is we're finding the area under the curve of the force displacement. As a change in position here, we can calculate the work as this is x2 minus x1 times the force would give me the work required. However, when we get into a force that's not constant, in this case follows a parabolic shape, we need to find out the total area under this curve. By doing that, all we really have to do is do an integration of the area under the curve, and that's going to give me the work of the system. An example I did here is I have a cable that weighs 2 pounds per feet as attached to a bucket filled with coal that weighs 800 pounds. The bucket is initially at the bottom of a 500-foot mine shaft. We want to determine the amount of work required to lift the bucket to the midpoint, and then lift from the midpoint to the top, and then to lift from the bottom all the way to the top. Now I noted here, since the force required to raise the bucket and the cable will decrease as the cable is raised, meaning as you raise this, you end up with less force because your cable is becoming shorter. So it won't require as large a force to raise it. So I can say, using the integral, that work is going to be the integral between 0 to 250, where 250 is the midpoint of the 500-foot mine shaft. We set that equal to fx d work. fx dx. Now, what the force is, or the weight, I got the cable that's 500 times 2, which I put in here, plus is 800. That's at the very bottom. And then we're going to minus the 2x dx, where this distance here is going to change by some delta x here. Alright, so all I have to do now is set up the integral, and I get 1800 minus 2x dx. The 2, again, is coming from the 2 pounds per feet. So when I integrate that, I get 1800x minus x squared. I put in the 0 and the 250, and I get 387,500 foot-pounds. And that's all you're going to do with a problem like that. That's where the force is going to vary. B, determine the amount of work required to lift the bucket from the midpoint of the shaft to the top. All you're going to do there is you're going to start at 250, go to 500. We do the same type of integration. In this case, we get 262,500. And then part C says to go from the bottom to the top. So as I go from the bottom, I will get 650,000 foot-pounds. Alright, so that's a good example of how to do how to calculate the work where the force is not constant. Now springs, again, as I apply a load to the spring here, that this force, as I displace the spring more, that the force is going to increase, because the force applied to a spring is going to equal to the minus spring constant times the displacement of the spring. So the work of a spring is always going to be the integral from the initial position to the final position of fx dx. So in this example, I've applied a force here. So as I apply a force, the spring will deflect or compress, and this object here will move back a certain distance. So I set this as my initial position. This would be my final position. So the work of the spring, again, is going to be the integral from my initial to my final of fx dx. But fx is defined as minus kx dx, as defined right here. I put that in. All I have to do now is pull out the k value. I integrate x dx, which will give me x squared over 2. I put in my xi and my xf, and I get this value right here. So to calculate the work of a spring, it's going to be 1/2 k times the initial position squared minus 1/2 k times the final position squared. Again, these are slightly different here in that you're doing initial and final here based upon what we did previous. Find that here. Previous, where we're doing final minus initial. So they're opposite regarding the springs. Okay, so that includes this little lecture. Again, just covered the basics of how to do how work is related to the change in kinetic energy, and the kinetic energy is just going to be the 1/2 times the mass times velocity squared for an object, or when you get into the spring, then the kinetic energy of the spring is just going to be 1/2 k times the displacement squared. Alright, hope that helps you guys.